So we're talking about heat again, but this time we're talking about phase changes. So what is a phase change? Well, I think you know what a phase change is, but you might not know the name phase change. Let's have a look. Solid, liquid, gas. When you're going from a solid to a liquid, that is a phase change. You talk about melting. When you're going from a liquid to a gas, that is a phase change. We talk about evaporating or vaporizing. And you've got also this process, which is less known, going solid straight to a gas, which is sublimation. And they go the other way as well. Going the other way from a liquid to a solid is freezing. From a gas to a liquid is condensing. And there is a reverse process for sublimation, which we would call vapor deposition. Okay, and now you don't need to worry too much about these. I'm not going to get into them. They're just there for interest's sake. But yeah, what we need to look at is the energy and what happens with energy in these phase changes. So let's first of all consider our graph of increasing temperature and increasing energy, because remember, when you have, say, a hunk of metal like aluminium, it'll increase in temperature and increase in the energy stored in that metal. Remember, the particles, according to the kinetic theory of matter, kinetic meaning it moves, as it heats up they move more, and more energy is stored as kinetic energy. But there's a point where that solid will want to turn into a liquid, and it'll take a certain amount of I think I've drawn this around the wrong way. Let's change it. Temperature on this side. But it will take a certain amount of energy this is E, it'll take a certain amount of increase in energy to melt it, turn it into a liquid. Once that amount of energy has been put into it, it will then start increasing in temperature again. Okay, and then once it gets to a liquid, it'll stop increasing in temperature. You'll have to add a whole lot of energy to it to be able to turn it into a gas, to vaporize it. And then it'll start increasing in temperature again once as you continue to add energy. So you can see that this is going to cause problems. For instance, if you have water and you want to raise it from let's say negative 10 degrees Celsius, and you want to make it go up to, say, 20 degrees Celsius. Our previous formula to find the energy stored in that was the mass times the latent, the specific heat capacity times by the change in temperature. Now the problem with this is that's not dealing with the total amount of energy that you use to cause this change, because there's energy that goes into it without changing the temperature. So even though it might go up, it's going to stop. It's not a constant linear graph all the way through. So we needed some way to work out what this part is going to be. And this gives us another formula to find that energy. And let's just do that in orange up here. And our formula is going to be Q, again, because Q is energy in these situations. And you might call it Q melting, just to distinguish it from the Q previously. And this depends on the mass as well, because the more mass you have, so 10 litres compared to 1 litre, you need 10 times the amount of energy to affect this change, to cause this change to happen. And then you need to know how much energy per kilogram of that substance is required. So we have this other constant which is related to the different substances, and this is the latent heat of fusion. Okay, there is also a latent heat for the other phase change when you're going from a liquid to a gas. Remember, this one is from a solid to a liquid, and then we go from a liquid to a gas. So there's what we call that one. It's also symbol L, but this time it's the latent heat of vaporization or evaporation. Okay, so you're turning it into vapor, so it's vaporization, or you're evaporating it, so you're turning it into latent heat of vaporization. In fact, vapor, evaporation, those words are linked, aren't they? I wonder how they're linked. Anyway, that's irrelevant to us. So if we're trying to work out the total energy from negative 10 degrees to 20 degrees, we'll have to do that change in temperature of 30 degrees using the top part, but we'll then have to add it to the energy required to melt it. And that's just, yeah. And we just, these things are constants here, so C is the is a number that's specific to the material, whether it's water or aluminium or could be rocks, whether a particular, maybe full of silicon. So I don't think it has to be one type of material, but that certainly makes it easier. You'd probably have to work out the proportion of the material, the different materials, and use each of the individual latent heats and each of their individual heat capacities to work out the energy that's required to change the temperature or to change their state. So let's just go through an example that's a little bit more concrete to help your understanding of this. We're going to consider, we always use a graph to represent these changes. It's just a bit easier for us. With water, which is starting at, say, negative, we'll use a negative 10. And then at 0 degrees is when it melts. And then again at 100 degrees it vaporizes, and then it keeps going up. So we'll say it goes up to 110 degrees Celsius, from minus 10 degrees Celsius. And so that's 0 degrees Celsius and 100 degrees Celsius, because it boils and evaporates therefore at 100 degrees Celsius and melts or freezes, depending which way you're going, at 0 degrees Celsius. So if we're trying to find the total amount of energy for water, H2O, to go from negative 10 degrees to 110 degrees, we need to use our two formulas here. Let's go into a different color. We're going to have to, the total energy is going to be M L F, which is the latent heat of fusion, which is dealing with this phase change, the amount of energy here. So we call that 1 because we're dealing with 1 on there. And then we're going to have to add to that the energy required here, which is 2, the energy required to evaporate it. So that's going to be the mass again, times by the latent heat of vaporization, or evaporation, depending what you want to call it. Just be aware that different people will use different names for these. And we also have to add to that the overall, the energy from these sections here, which deals with just the change in temperature. Okay, so that's going to be MC, which is the specific heat capacity, times the change in temperature. And yeah, so let's see. I'm not going to give you specific numbers. It's I don't know them off the top of my head, and we'll just fumble it. But I'll just tell you that if we had, say, 10 grams of water, that starts out as ice, it goes to water and then goes to gas, water vapor, that mass would be 0.010 kilograms, and that's what we would put in here, here, and here. The change in temperature is total is 120 degrees centigrade change, and that's what we would put in there. And we would be given these 3 constants, and we would just plug those in. And remember that we're adding each of the individual sections. We'll add them up to find the total Q, and that's how it's done. Okay, again, it's a formula. Make sure you're understanding what the meaning of these different parts are. This is kind of complex too, I have to say, for level 1, so if you're struggling with this, don't be worried. Just take your time with it and make sure you understand what the graph means, what the flat bits mean, and how energy relates into all of these situations. Once you get that good understanding of what's happening with energy, this formula will make much more sense. Okay, all the best with it.